In section 5.3, the Pythagorean theorem and its converse, students will understand how to use the Pythagorean theorem and its converse. So we've got 5 different success criteria that we are going to make sure we know how to do to be successful in the unit. We need to be able to state the Pythagorean theorem and when it can be used. We need to be able to simplify radical expressions. This is what we practice in class. We need to be able to use the Pythagorean theorem to find the length of any side of a right triangle, either a leg or a hypotenuse. We need to be able to use the Pythagorean theorem as part of the process of calculating area. So perhaps we need to find a missing side. We're going to use the Pythagorean theorem to help us find that side so we can find the area. And then we also need to be able to use the converse of the Pythagorean theorem to classify a triangle as obtuse, right, or acute. So let's begin. Of course, we know the Pythagorean theorem. We've used it already this year, and it says the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. So A and B are the legs. So if we square them, in other words, if we get A squared and B squared, and we find the sum, we add them together, A squared plus B squared, that's going to equal the square of the hypotenuse, C. One thing that's important to remember when working with the Pythagorean theorem is that the hypotenuse is always C. It doesn't really matter which sides you define as A and B, the hypotenuse has to be C. All right, so let's look at an example. Let's find the missing sides. In this case, there's only one missing side that we have to find, and it's right here, that side's X. I really should have done a better job and put in 2 congruent marks in this triangle so that we knew that these 2 sides were congruent. And then what we're going to do is we're going to trace the sides, sort of. Okay, that was terrible. We're going to try to trace the sides where we saw a right triangle here. And this is not much better, but work with me here. We're going to trace the sides of that right triangle, and now let's fill in the information here. So we got 3 sides of a right triangle. Okay, so we know this here is a right angle. We want to find this side X. We know this whole length was 12, which means this side has to be 6, and my hypotenuse is 10. Now remember we said A, B, and C. C has to be the hypotenuse, the side across from the 90. So maybe we'll set up A and B like this. So if we think about our formula, A squared plus B squared equals C squared, plug in the values we have. A is 6, B is X, and C is 10. Now let's simplify it. 6 squared is 36. 10 squared is 100. And so to solve for x squared, we have to get rid of the 36. So we'll subtract 36 from both sides. That's going to leave me with x squared equals 100 minus 36, which is 64. Now this is a nice problem because to undo the square, we have to take the square root, and 64 is a real nice square root. The square root of 64 is 8. So in this case, x must be equal to 8. Let's do another example. Let's find the missing side we see here. In this case, we're trying to find x. But if I look at this triangle here, where x is one of the sides of the right triangle where x is a side, I don't know this side right here. So let's start by finding this side, and I'm going to call it y. So if we look at this other triangle, this other right triangle, this side is y, this side is 3, and this side is 3 root 2. Now let's label our sides A, B, and C. C is always across from the 90, so 3 root 2 has to be C. Then either of these can be A and B. So here's your formula. A squared plus B squared equals C squared. Now let's plug in the values. A was y, so y squared plus b was 3. So y squared plus 3 squared equals c squared, which is 3 root 2 squared. So let's simplify this. So we're going to have y squared, 3 squared is 9, and 3 root 2 squared. Remember, that means 3 root 2 times 3 root 2. Multiplying like terms here, we're going to have 3 times 3, which is 9. Then the square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is 2. So now we have y squared is y squared plus 9 is equal to 9 times 2, which is 18. Solving for y, we would subtract 9 from both sides, and 18 minus 9 is 9. So if y squared equals 9, take the square root from both sides, and the square root of 9 is 3. So now go up to your diagram, and we can fill in this information that y is equal to 3. Now we're going to use that to help us solve for x. Get some more room here. Now this time my triangle, still a right triangle. We knew one side was 3, one side was 8, and we were trying to solve for x. So let's label our sides A, B, and C. Hypotenuse is across from the 90, so x has to be C, and 3 and 8 might be our A and B. Okay, so setting up A squared plus B squared equals C squared, we'll have 3 squared plus 8 squared equals C squared. 3 squared is 9, 8 squared is 64, and then we have C squared. So 9 plus 64 is 73, and then we want to take the square root of both sides, so C is equal to the square root of 73. We should check to see if we can't simplify this, but the square root of 73 doesn't simplify. So we're done. Let's talk about the converse to the Pythagorean theorem. The converse of the Pythagorean theorem helps us figure out what kind of triangle we might have. So if it turns out that c squared is equal to a squared plus b squared, then we know the triangle has to be a right triangle. And it's worth noting here that c has to be the longest side. So you might want to add that into your notes. C is the longest side. So if whatever C is the longest side, if that's equal to the square of the other two sides, the sum, then you know your triangle has to be a right triangle. But what if it's not equal? Two other possibilities. So if that quantity, C squared, is greater than A squared plus B squared, then your triangle has to be obtuse. One of the angles has to be greater than 90. But if C squared is less than A squared plus B squared, then your triangle must be acute. So let's look at an example of that. Okay, so let's classify the triangles. My sides are 38, 66, and 60. So in this case, the longest side here is 60, so that's going to be my C. So I can let 48 be A and 36 be B. So we're going to check, does 48 squared plus 36 squared, well, we're going to see how does that compare to 60 squared. That's our question. All right, so I might need a little bit of calculator help here. So let's see here. Let me get a calculator out. I don't happen to know 48 squared off the top of my head, but I should, but I don't. All right, so we want calculator. All right, there we go. So here's my calculator. So we're going to do 48 times 48. And so that's 2,304. All right, so we'll go here. 48 squared is 2,304. Now we have to find 36 squared. Get our calculator back again. 36 times 36 is equal to 1,296. So 1,296. And we want to check, does that equal 60 squared? Well, 60 squared is 3,600. And sure enough, if I add 2304 plus 1,296, I get 3,600. So 3,600 equals 3,600. That tells me that this must be a right triangle. Let's look at the second example. Now this time we know our sides are 5, 9, and 6. Remember, you have to let C be the longest side. So 9 has to be our value of C. A can be 5, B can be 6. So we want to compare, how does 5 squared plus 6 squared compare to 9 squared? All right, so this one I can do using mental math. 5 squared is 25. 6 squared is 36. How does that compare to 9 squared, which is 81? So then we add 25 and 36, and we get 61. I'm doing math, Calvin. What are you doing?
I'm staying here and watch you.
Okay, you stand here and watch me. Calvin, which number is bigger, 61 or 81?
81.
81 is bigger. That's right. So in this case, it turns out that C squared was bigger than A squared plus B squared. And so that means that my triangle must be obtuse.
Yes.
Yes.
Yes, Mom.
Yes, very good.
Yep. My ball is orange.
All right, so the last thing I wanted to go over is a few Pythagorean triples. Pythagorean triples are when you get nice whole numbers that you can plug into the Pythagorean theorem. So 3, 4, and 5 are nice whole numbers, aren't they?
Yep.
And it turns out that 3 squared plus 4 squared is equal to 5 squared. Let's check it out. Let's try and see if it works. 3 squared plus 4 squared is equal to 5 squared. Does it work? 3 squared is 9, 4 squared is 16, and 5 squared is 25. And 9 plus 16 is equal to 25. So 25. So 25 is equal to 25. So 3, 4, 5 is a right triangle. But it also...
But there's one.
Yep, there's one. Also turns out that any multiple of 3, 4, and 5 will also be a right triangle. So for example, if we took 3, 4, and 5,
What's your phone?
and we multiplied each of the numbers by 2, we would still get a Pythagorean triple. So 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. And it turns out that 6 squared plus 8 squared is equal to 10 squared. 6 squared is 36, 8 squared is 64, and 10 squared is 100. And sure enough, 36 plus 64 equals 100. So any multiple at all of 3, 4, and 5 will always give me a Pythagorean triple. So 3, 4, and 5 works. 6, 8, 10 works. If I multiply by 3, you could have 9, 12, 15. If you multiplied by 4, you could have 12, 16, 20. And so it's really helpful to learn to recognize multiples of 3, 4, 5 because 3, 4, 5 triangles show up all the time. Again, this is a real classic example of stuff that shows up on SAT or ACT or maybe even the Ames. All right, so here's just a few common Pythagorean triples that I want you to be familiar with. Quiz yourself. 3, 4, 5. 5, 12, 13. So 5 squared is 25. 12 squared is 144. And 13 squared is 109. And sure enough, 25 plus 144 equals 169. 7, 24, 25. And 8, 15, 17. If you recognize any of these, and you happen to see 2 out of the 3 sides, it kind of saves you a little bit of work to find the others. So for example, if I knew the longest side here was 5 and this side was 3, I could save myself a little bit of math and realize, oh, this has to be a 3, 4, 5 right triangle. In another example, if I knew that let's say the hypotenuse was 4 and this side was 3, I cannot assume that the other side is 5. That makes no sense. The hypotenuse has to be the longest side, so if it were going to be a 3, 4, 5 right triangle, the hypotenuse would have to be 5. But in this case, it's 4, so this would not be an example where you could use a Pythagorean triple. All right, that's it. We will do some practice problems in class on Wednesday.